Hello and welcome to the next lesson on forces. This lesson is lesson 2 in the Year 7 forces topic, and we're going to be looking at mass and weight and the differences between them. My name's Mr. Pratt and I'm Director of Science. For the lesson then, you're going to need a pen, some paper or an exercise book. We've got a couple of calculations to do as well, so you're going to need a calculator. Unless you're needing to watch this video on your mobile phone, get it switched off on silent, turn it over, and try and avoid any distractions that you can. A recall starter for you.
Laura, when you do this, did you go down slope?
I want you to write down why astronauts jump more easily on the moon than they do on Earth.
I'm having... This is the best way for me to travel, uphill or downhill. What's that? Like this, two-legged hop. And on level ground, I can skip. I don't like that loping thing. Oh, the loping's the only way to go.
Checkpoint.
See, when I'm on level ground, I can skip. But this two-legged thing is great. Man, I can cover ground like a kangaroo.
Well, I'm hoping that you've written something down that's to do with gravity. So 1 mark if you've just mentioned the word gravity. If you've said there's less gravity on the moon compared to the Earth, that'll be pretty much spot on. If you've put there's no gravity on the moon, that wouldn't be right. And if you've put anything to do with air or air resistance, that would make a tiny bit of an effect if you were moving forwards, but not on the amount you can jump up there. First objective then is to make sure that you're able to describe the difference between mass and weight. The 2 words that we often confuse in everyday language, so we need to make sure that we get them spot on. And then we're going to calculate the weight of objects from the mass, and we're going to do it on Earth, and we're going to have a look at what the difference would be if we were in different places on different planets. 2 minutes then for a starter, and this is looking back on work that you should have covered in primary school. So question 1, what does gravity do? Question 2, is the gravity on the moon? We've touched on that a little bit already. And then number 3, is the gravity in space? Just a minute left. If you're finished, we could add an extra number 4, and you could ask the question, is there gravity if you're in orbit around the Earth, like on the International Space Station? we're finishing off. Number one then, gravity might not quite work how you think it does. You probably put something down about pulling us down, and that's fine. It's a reasonable starting point for an answer. So it will pull objects together that have got mass, so it'll pull them together. It's an attractive force. We normally experience it pulling us down towards the Earth, and because the Earth is so much bigger than us, we only really notice the pull on us. But gravity will pull all objects together, so gravity will also attract the Earth towards the Sun, and because it's got some motion already, it'll continue in orbit, so it's a force between two objects. Number two is the gravity on the Moon. Yes, there is. It's a lot less than it is on the Earth, because the moon itself has got a much smaller mass than the mass of the Earth has, so there's less gravitational force there. And number three is the gravity in space. If you're completely in the middle of nowhere, it's pretty much zero. As you move away from an object, the amount of gravity decreases, but there is tiny amounts if you're anywhere near an object. And if you added yourself a number four, if you're in orbit around the Earth, say in the International Space Station, there will be gravity, but it feels as if there isn't, because you're in a continuous state of falling, and we'll cover more about that when you get up to Key Stage 4 on GCSE. So The Simpsons, they've always been a massive hit. Marge. So Marge has got a mass of 60 kilograms. Maggie's got a mass of 10 kilograms. Lisa's got a mass of 25 kilograms. Bart's got a mass of 35 kilograms. And Homer's got a mass of 130 kilograms. So mass then, let's make sure that we get mass right. So mass is always measured in kilograms, or it could be grams. But kilograms is the number that we're going to be using when you put into equations in physics, so it's always measured in kilograms. It's a measure of the amount of something that you've got. So it's, if you like, it's adding up all the mass of the individual atoms that we're made of, and we end up with the mass of an object. And mass doesn't change depending on where you are. Unless you do something dramatic, your mass is going to remain the same. Just by moving, by going to a different planet or going into space or going to a different place on Earth is not going to change your mass. So then Homer. What's Homer's mass now that he's in space? Homer's in space, he's in the middle of nowhere. Well, Homer, your mass doesn't change. It doesn't matter where you are, your mass stays the same. So Homer's mass is going to stay at 130 kilograms, whether he's on Earth or whether he's in the middle of space. The only way that he could change his mass, well, eating those peanuts would change his mass, because then he'd have the mass of him and the peanuts. So the Simpsons now are waiting for the favourite TV show to start. Weight's a force that's caused by the gravitational field. So all forces are measured in newtons. So if we mark an arrow on here, we can show the weight of everybody. I've drawn bigger arrows if the weight is bigger. So Homer's got the biggest arrow. So weight is a force. So weight will change. It depends whereabouts you are. If you're in a different gravitational field, that's just the way that we describe the gravity around an object, then your weight will be different. So mass stays the same, but weight depends on the gravity that's pulling you down. Go back to Homer again. So what's Homer's weight now that he's in space? So weight depends on the gravitational field, but Homer's in a place where this is zero. So let's imagine he's in the middle of outer space and he's nowhere near anything. So his mass will stay at 130 kilograms, because mass doesn't change, because it's to do with the atoms that you've got, it's the amount that you've got. But because gravity is now zero, Homer's weight's zero. So he's weightless. Still got a mass, but no weight. To summarise then, weight's the force acting on an object due to gravity. So we put that in newtons. And the weight of an object depends on the gravitational field strength. If you want, you can just use the word gravity instead of gravitational field strength for now. And the mass of the object. So objects on the moon weigh less than objects on Earth because the gravitational field strength on the moon is less than it is on the Earth. It's less than a fifth. Homer again, standing on the Earth. That's not to scale, that diagram. Homer's got a mass of 130 kilograms, assuming he doesn't carry on eating that donut. So his weight is the force on Homer from the Earth's gravity, pulling his mass down. So the gravitational field strength on the Earth is about 10 newtons per kilogram. At GCSE, you'd use 9.8. But we're going to use 10. It'll just make your calculations slightly easier that we're going to do soon. So if the gravitational field strength is 10 newtons per kilogram, it means every kilogram of Homer is being pulled down by 10 newtons. So Homer's weight will be 130 kilograms times 10 because it's his mass times gravity. 130 times 10 is 1,300 newtons. So Homer's weight is 1,300 newtons. His mass, 130 kilograms. His weight, 1,300 newtons. So that's the equation that we can use. Weight equals mass times gravitational field strength. And we've got the weight in newtons. The mass, we've always got to use kilograms, don't use grams. And the gravitational field strength is the amount of newtons per kilogram, and that'll vary depending on where you are. Here they are again. Weight equals mass times gravity. Gravitational field strength is about 10 on Earth. And what I want you to do is calculate the weight of Marge, Maggie, Lisa and Bart, just like I did with Homer. 2 minutes, off you go. Just coming up to halfway through the time. Should be at least on Lisa by now. Should be nearly done. Give yourself 1 mark each then, so it's going to be out of 4. So the answers, Marge should be 600 because it's 60 kilograms times 10 newtons per kilogram. So you times Marge's mass, 60, by the gravity on Earth, which is 10. Maggie's 100, 10 times 10. Lisa's 250, 25 times 10. and Bart's 350 newtons, 35 times 10. Don't forget to put the N for newtons after the number. If you've only put 600 and not 600 newtons for Marge, just give yourself a half. Must remember that's really important. Going to look then at how gravity varies in different places, and we'll look at the planets in the solar system. So different planets have got different strengths of gravitational field. The bigger the planet, if it's more massive, if it's got more kilograms, then it will give a gravitational field. But also the density of the planet has an effect. So if it's more concentrated, it will make it stronger, the gravitational field stronger. Let's imagine that you're travelling around the solar system and you're going to different planets and you've got this container of food. You don't open the container so you don't lose any of it, but its weight would change depending on where you are. So its mass stays the same, its weight changes. And we work weight out by doing mass times gravity. I've given you a little summary there of the gravitational field strength in 5 different places in the solar system. The numbers aren't exact there. For example, we've put the Earth to 10 newtons per kilogram. It's actually nearer to 9.8, but I've just done it to a whole number. I'm going to give you 2 minutes and I want you to calculate the weight of a 0.5 kilogram bag of donuts. So I've told you the donuts has got a mass of 0.5 kilograms and I want you to find the weight in the 5 different locations. halfway through your time. Time's up then. So again, give yourself a mark. So on Earth it's 5 newtons. Done 0.5 kilograms times 10, 5 newtons. Moon 1 newton. Jupiter 12 newtons. Mars 2 newtons. And Saturn 4.5 newtons. Well done if you've got them right. Don't miss off your end for newtons. So they feel very different. So your bag of donuts, the same mass, it's the same amount of donut, would feel very different. If you look at picking up your bag of donuts on Jupiter compared to the moon, then would feel 12 times heavier, 12 times the weight, but it's still the same mass of donuts. It's just that gravity is 12 times stronger. If you can write a sentence explaining what the difference between mass and weight is, then we've nailed that. So I'll just give you a few seconds, just be writing it down. What's the difference between mass and weight? Okay, have you managed it? So mass is the amount of substance in kilograms, and it stays the same. Weight is the force of gravity on that mass, and the weight can vary depending on what gravity is. What I've done here now, I've got 2 columns, and we've got the units, that's the thing that we measure something in, the thing that we put after the number, but the weight and the mass, they've got mixed up. So what I want you to do is to sort them out, and underneath weight I want you to write down the ones that measure weight, and underneath mass the ones that measure mass. They're not an equal amount in each of the 2 columns. There's more in one than there is in the other, so don't let that put you off. Now you will have done really well if you get these right, because there's a few weird things in there like pounds and stones and ounces that are old-fashioned. We call them imperial, that your grandparents probably be more familiar with. So there we go. For weight, we've got newtons, kilonewtons, which is 1,000 newtons, and millinewtons, which is 1,000th of a newton, like millimetre is 1,000th of a metre. And then on the mass side, we've got grams and kilograms. Remember, kilograms is the one that we put into our equations in physics. Milligrams That's a thousandth of a gram. You'll see that a lot on food packets. Pounds, stones, ounces, they're the old units, are all measurements of a mass. So if you're buying some sweets, we used to buy sweets in ounces, you'd be buying a mass of sweets, a certain amount of atoms in the sweets. And then tons, spelt TONNES, is 1,000 kilograms. What I want you to do now then is to decide whether it's mass or weight which fits with the sentence A, B, C, D, E and F. You don't have to write them out. You could just put M and W, so you could write A, W, if that's your answer. And I'll give you 2 minutes and then we'll mark them, see how you've got on. Just going up to halfway through your time. Give yourself a mark out of 6 then. So constant, no matter where you are. I think that's supposed to be a pun there, no matter where you are. So it stays the same, so that's mass. Changes when gravity changes, that's weight. Measured in newtons, that's weight because it's a force. Measured in kilograms, that's mass. Depends on the amount of matter present, so that's mass. And depends on matter and gravity, that's weight. Well done if you got that right. If you've got more than 1 or 2 of them wrong, just go back and have a look at it again. It's something that's going to be really important all the way up to GCSE. One last thing. Homer decides that he's going to treat his body as a temple, and he works out for 6 months straight. So there's the before and after. After 6 months, his new weight is 1,000 kilograms. If he stayed on Earth, what must his mass be? If you're struggling, bit of a hint. Weight equals mass times gravity. Gravity, if you remember, on Earth is about 10. So 1,000 newtons equals Homer's mass times 10. So Homer's mass must be 10 kilograms. Well done if you've got that right. There's a little summary then. If you want to record some extra notes in a notebook, because you've not done it so far, just pause the video. We've got the main points on that. We've got explain about what mass is across the top, what weight is across the middle, and then we've got that equation that we use for finding the weight from the mass. Goodbye, I'll see you next time for another lesson on forces. Well done.